stelle mich kurz selber vor, habe nicht wie der Vorredner eine eigene Folie dafür. Mein Name ist
Some information about myself, Stephan Rolfes. I'm coming from Beuth-Hochschule in Berlin. I think Beuth-Hochschule is something that you're mostly familiar with, Beuth University. So what we actually do is we train theater and event technicians. We actually have 3 study courses to do that. We have 2 bachelor degrees, one for theater and one for event manager, and then one master degree, obviously also in that degree course. And then we both of all provide training for technical service providers, and obviously these people will then be recruited by agencies, and that is the people that the creative house will then need to deal with. We've just seen the charts, that the creative idea comes from arts, comes from the creative sector, and then very, very quickly it is about the budget that usually slows down things, and then before the authorities put a stop to things, then it's usually the technicians, and that is the people coming from our university. So I'm basically teaching constructional science, so everything to do with constructions is what I do. But I also take good care of the technical security and safety security, and apart from being a professor, I'm also an expert of Bundesunfallkasse, and I'm actually checking things that are also, above your heart, so you can see firmly attached to constructions, but nevertheless, you basically sit down, and then obviously you hope that an expert checked that for you and that everything is all right, everything firmly fixed to what we see above our heads, and that is obviously very, very important. And when it is about the design and the construction of these kinds of systems, so that again is not about mechanical equipment here, that is only about some fixed constructions, but when it is about the design of mechanical equipment, there's obviously a couple of issues that have been discussed for a couple of years already, and that has actually found its way into the regulations. But nevertheless, people in the regulatory circles were not quite sure about what they would actually be doing when that sentence was actually introduced to the regulations. I'm also a member of that regulatory circle, and I have to blame myself because obviously that is a circle of experts discussing a lot of things, and then basically that leaves a trace behind, and then usually only afterwards you realize what it is that you actually did. It might sound a bit evil, but that is really the way it is. You don't really know things, in advance. And one point is actually this situation and how you deal with that when you have problems, when you have accident strains. And then I was wondering, I'm designing a construction, I calculate it, and then I want to put that up and connect that to some mechanical equipment. So you basically develop something and then put it in, and then you think, okay, there is this kind of chain thing that can actually do it, and that is the loads, and I just put that down. There's a chain hoist that you connect, and then you say, okay, they want to do that during the show, so you want to actually improve security and safety so it is moving. But what happens if it doesn't move the way you want it to move? So especially when it is about the machine actually having a problem, and then that problem might actually lead to some peak loads. So what is it that we do with that kind of situation? That was our starting point. And what I would like to introduce to you today is actually a couple of research findings, on the one hand coming from our university, because we have been dealing with that for something like 3 years. So what are we actually doing about requirements that are being defined in regulations? So that is on the one hand about the constructional designers, engineers that develop the equipments, but then it is also about the technicians that will need to deal with these systems, and then again the constructional engineers that basically work with constructions, because there are no constructions. So mechanical equipment has a lot of standards and norms. There's a norm for everything, the cable, the socket, and all of that basically comes with the regulation. But what you connect to that, would that actually be something that is going to hold true? Is that the LED monitor is the fastening correct? But there's no standard on that. The manufacturer says, okay, that is what you do, and that is what you then deal with. So that was really the first point of my presentation, what lies ahead. So why are we actually dealing with that? Because it's a question that comes up again and again. We need some theoretical basics. So I'll try to be very, very brief. But nevertheless, we have to define a couple of terms. And being an expert, I see that again and again, that the terms are totally mixed up, are totally confused. People talk about nominal loads. Other people talk about things that can actually be carried, load capacities, and we have a standard that is actually DIN 56950 that was actually amended last year. And it is very, very important to understand what the difference is between a nominal load, between a load capacity and accident strain. There's a lot of calculations also in my presentations. Try not to be shocked. We'll be very, very brief. Mostly I have included them for further reference. So obviously you can all come back to me and contact me, and also I can easily send out the handout by email, and then obviously you can read about that kind of thing, and that is people that might actually be interested in. So it's a lot about engineering sciences and that kind of thing. And then there were also a couple of test runs that we did. They are very, very new, so we talked to some graduates. So we actually did that. So that is somebody that just passed his final examination, and therefore I could just introduce them to our finding, and it's extremely interesting what you'll see. Obviously, I'll also come up with a forecast. So why am I dealing with that? I've mentioned that already. It's a question that comes up and again and again. I come into a theater and then there's people there, or could also go into a technical plant, and then we take a look at the equipment, at the system, and then I basically disturb what the system is doing, because being an examiner, obviously I have to make sure that I'll see what the problem might actually lead to in case of accidents and incidents. So I say I have to make sure, is the system doing what it does? So I want to make that safe. And then there's a big bang, and then you feel, okay, that gives you that kind of thing. And then people don't know that, because usually operators only use it in a regulated way. It has a very soft starting point. It's very soft, very easily working. And then the experts are coming in, and then the system is doing different things. And then the hoist, they were actually coming up and down in a very synchronous way, and now they're half a meter apart. And then you think, oh my God, what happened? So all of that does happen, ladies and gentlemen. And against that background of acceptance tests and recurring tests, that is what you do as an expert. And you have to do that for operators. They are obliged to do that. And also when it is about the new design of mechanical equipment, then usually there is a so-called pre-test. I'm not quite sure if all of you are actually quite familiar with that. There's a pre-test, and that basically tests the calculatory approach. So if a chain hoist is being developed, a stage is being developed by a manufacturer, then the manufacturer hands in the documents, and they did their calculation, and the expert needs to check that, and then they have to say, okay, it works. It is basically like an examiner statistician, in supervisory building law. And then you think about, so how did you basically calculate the accident strain? What about the loads that were applied? And then I've been mentioning already that that was actually the reason for us to take a look at that. So what is the standard that we deal with? That is DIN 56950. It is basically the wording of 2005. We had a definition of the sizes that are relevant, and they basically refined that kind of thing, and they try to be very, very clear. And they were saying you need the safety factor 2. That is usually what they say, and that's what is not right. You don't need factor 2. You actually need to design for twice the nominal load. Nevertheless, in the calculations, you still have to calculate for safety scope. So therefore, that is not a security or safety factor. Therefore, it says twice the nominal load. That is what you want to design for. That's a very important difference between a safety factor and between what you actually calculate with, because everything that is happening in the calculation needs to go on and is based on different kind of safety factors and needs to be calculated. So that is the general part. That is what was actually defined. It's getting more specific when it comes to load-bearing constructional elements, and then they're also mentioning the same term again. So again, it is about double nominal load that you need to design for. And then it actually is about that little sentence that it all started, and that is the sentence I mentioned already. It says something like, in accidents such as power failures or engine control unit failures or pipe bursts, the plant components must be designed for simple accident strain. Then you think, okay, you have to calculate for that. So that was quickly worded. So what could accident strains be? I mentioned that already. That is power failures, or it could be a burst pipe, it could be oil loss, it could be pressure loss, it could be control unit failures and things like that. That is what we talk about. And then there is obviously the engines, the term of the engines. And again, we have that kind of approach, that kind of philosophy of intrinsic safety. We actually call that over-dimensioning. So you actually have twice the strain, and that is then what you achieve in terms of safety. And again, it says something about twice nominal load, especially also when it comes about floor lifting systems. And again, it gives you that sentence: for instance, all engine parts between the load lifting device and the security parts must be designed for simple accident strain. And that is usually the brakes, the safety elements, that is usually the brakes at the end of the force chain, and they are then to stop the load, because all regulatory forces and all sensors and all intelligence is no good, all measurements are no good. If you don't have anything that actually holds the load, you can recognize, okay, it's going into the wrong direction, it's much too fast, it's all not right. You can recognize all that, but then you need a kind of element that stops the whole thing. And that obviously is what the safety securities are doing, and that is the brakes. So all parts between that obviously therefore need to be calculated and designed in an appropriate way. So then 2012 we had a revision. There was some rewording because obviously people noticed that that approach causes a lot of problem, that actually led to a lot of misunderstandings. And then they were saying that there's one reason, and then there's another reason in the Germans being very fond of standards, and we obviously have European partners in that as well, and we basically try to come up with an international regulation, international standard. So obviously we are very much interested in expanding DIN 56950 to the international level, and we would like to turn this into a European standard that is also widely used in other European countries in terms of mechanical equipment. And against that background, there was a lot of rewording. And again, we have the general point, and for the calculation of load-bearing constructional elements within the system limits, and we talk about the system limits in a minute, and then again we talk about incidents. Again, we actually talk about the simple accident strain, and obviously, especially under high speed, it can exceed the value of double nominal speed. I think we will need to discuss that sentence again, because our findings now found already lower speeds can lead to an exhaustion of the value of the nominal speed. So we actually saw that in our test runs. And again, you can see that same definition for the engines. It is all the same. True, again, the 400 hours of operation, and then again, a double nominal load, and then incidents and accidents. Again, the simple accident strain that needs to be assumed. So that was obviously a lot of text that I mentioned. So what does that actually mean? What does that actually mean? That kind of accident strain, what would that actually mean? There is a definition for that. That is actually defined here. It's a sum of the capacity load plus the dynamic forces that would actually occur in an incident. So it is actually the capacity load. I think, do we know what that is? I'll show you in a minute. But again, you have to add the dynamics that actually happen or occur in a problem. And you might actually see the problem. So what kind of dynamic forces come up in an accident incident? We'll take a look at that in a minute. So when is that happening? Again, I'd like to remind you, obviously, if you push the emergency stop, that is that kind of thing. But then there's security elements that respond, that could be over dimension, or a kind of rope is not rightly fastened, or you have different kind of panels, and then the panels need to stop in order for the foot not being damaged. So that might actually be accidents. That could actually be power failures, phase loss, things like that might actually happening. And then there is annotation too, which is very important. There is the stop category 0. That actually means that you stop power supply immediately. That is usually the worst category, and that is obviously what we're very much interested in. A lot of operators are not aware of that. They have no idea how evil their systems could actually react, because usually it all works fine, and then it's all very soft or very easily going, and then it's all very nicely positioned, but they have no idea that if you have a very, very big emergency, okay, I do admit it's very complex, it doesn't happen a lot in complex situations, but in simple systems, there might be that very much emergency-like problematic issues. That is actually, again, the DIN 56950. You can actually see that, again, that is obviously normal operation. That is obviously the nominal load. The 500 kilo hoist comes with 500 kilos. And then if you want to have the Newton, that is a factor 10, so that is 5,000. Then you might actually then have the weight of the load lifting device, any kind of stage that you connect it to, that is 100, 120, 150 kilos. So that is what you need to add. So that is obviously the loading load. That is basically what the engine has to cope with. So they have to lift the two things. And then you have dynamic forces that are added. And then there's some kind of acceleration. During acceleration, there's inertia. Weight doesn't need to move. So obviously, it contradicts that kind of movement. Again, that actually generates forces. And also the other way around. You're on a car and somebody wants to push that car forward, and then we fall down because we don't really want to react the same way than the car. So these forces need to be considered as well. And that actually leads to the nominal load that the whole drive needs to be created for. And then obviously we also have the incidents, the accidents, and then we have the same thing. We just have the dynamic forces that actually come into play as well. And then obviously you have accident strain that you arrive at in the end. You just remember what we've been talking about, but we actually heard something about the new norms that already included something like system limits. And there has been a very long discussion in our working group, in our standard working group. So where do we start? Where do we end? And it's very, very important also for the evaluation of risk. So where do you start with your system? Where does my system start? Where does it end? And that limit needs to be defined. You can only be responsible for something that happens within your system limits. And there's a lot of discussions, there's a lot of misunderstandings also in that field. In event management, you actually see that a lot. So you have that force that you put to two chains hoist. Is that then part of the mechanical equipment, or is it a decoration? Is it the load? So what exactly is it? So that discussion is coming up again and again. And therefore, we actually came up with a couple of drawings that try to explain that, or this kind of lifting point. You know, you put a kind of chain hoist to this kind of thing. So is that now part of the house? So is that also now the double accident strain or the double nominal load? So what is it that you now need to calculate for? So there's a lot of discussions that come up because the system limits are not clearly defined or not clearly understood. So that is the complete mechanical equipment here. And then obviously there is the load supporting device, there is ropes, there's bands, then there's different rolls. There's obviously then also the engine that moves the whole thing. And then obviously you can see the load supporting device, that is what you can see on B. Then the engine is C, and then obviously the load lifting device is D. And obviously you now know that you have the system limits that you need to adhere to, and then you need what kind of evidence you need to find for a lifting device. For instance, you have the lifting tackle of the traction rod, so not actually the connecting point to the traction rod, because I talk about the mechanical equipment now. So what you need to put to that is up to the operator. So my norm is only about the system limit, but obviously the traction rod, or also if it is a kind of transverse system, you have to deal with that. That could then actually be different kind of hooks are not allowed, but you know, a kind of quick chain link that comes into that then also comprises the engines, the motor shafts, and all that. So that is the introduction of what this is all about. And then what is important as well is obviously something that is very interesting for the people that apply it. So what is the design? So is that very theoretical or is that very practical? So usually the applied engineering sciences very much work with empirical data. So if we actually design a plant, a system, then we base it on empirical data. We have a lot of charts, we have a lot of information, we check a lot of things, we actually check for applicable levels and values. That is a very, very feasible way, and that has been tried and tested in engineering sciences, and that worked out fine. And then therefore it's not only about calculation that we talk, but we also talk about interpretation, about selection processes a lot. And also you can base that on test runs. So let's talk again about a manufacturer of an LED wall or a monitor or something like that. Let's assume they did a lot of test runs, kind of loadability tests, and they know, okay, that's what you need in terms of thread sockets. They actually will be fastened like that. You don't need to add another sheet. And obviously that is going to be fastened securely, and without an analysis they might actually be fine, and then they might actually be best assured that is the load that you can apply, and that is what it needs to attach the monitor. The same is actually true also for beamer fixtures. We have some work on that if you're interested. So obviously we're still working on that as well. So let's talk about the nominal load again. So it is quite easy to do it for that. So the nominal load is something that you know, and you're very certain about that, because you basically agree that you tell me what you want to attach, and then I say, okay, you just add that lifting device, and then I say, okay, you have to have a control unit. Is it going to be a soft start? Is it going to be a different start? You can define all that, and then you start calculating, then you can start selecting whatever you need, and then you arrive at the values that you need in order to find out what is happening during the drive. So what is happening in accidents and incidents? That is when it turns out to be quite problematic. You remember these forces, you know that, and that is something that you don't know. That is the dynamic forces in problems. That is what you know when it all works out fine. Then you know that also from the manufacturer, but you don't know what the dynamic forces are like when it comes to problems. So again, you know the nominal load, you know about the dynamic forces in normal operation, but you don't really know what it's like when you enter into a problem. So where do you get that kind of information? I want to add that just for hydraulic engineers. So hydraulic drives will be different in terms of accidents and incidents. I'm not going to talk about that, so let's talk about electrical drives for the purpose of the study. And again, the norm has told us there is the accident strain that is biggest in stop category 0. That is when you cut the cable, when you put the safety valve out, and if you cut the power supply to the engine, and then it just gives you a stop straight away. You try to bring that thing to a stop. So what are causes for that? So usually that is when it is about intelligent or complex things, phase loss, power loss. Apart from that, it doesn't really happen a lot. So very often that doesn't happen because now we actually have a lot of very intelligent systems. You have to be very, very careful with that kind of thing. Is that something that is permitted? So if you have 80 motors that actually pull a very, very complex load, then the other engines need to be able to compensate that kind of thing. That's very important also for theaters. If you have different kind of lifting hoists and then you use them, and also when it is about higher speed, so you have to get this right. So is this something that you want to do, you know, cut the power supply, or maybe also in a problematic situation, you might want to actually maintain a very good system that actually brings down the system in a regulated way, in a very soft way, so that you basically don't really cause peak loads or problems in other points. And therefore, it only says it is only possible if there is no other risk being caused by that kind of thing, because if that kind of thing happens, then you're not allowed to actually come to an immediate stop. So what is happening? You cut the power supply. Usually the engine stops very, very quickly. So there's no moment anymore, there's no power anymore, the brakes come in and the whole thing comes to a stop. So if you have regulated engine that is quite well, so you have a frequency converter that basically allows you to convert speed, and then the brakes can actually hold the load, and then basically moment is being created, and then the load is electrically being maintained because of that converter. And that is also very important if you actually interrupt the power supply, because that kind of frequency converter is not actually tension-free immediately, but it has a kind of interim circuit that actually comes in, and that moment is still being maintained at the engine before actually the brakes basically fall in with a load. However, those systems that actually cause the accident strains are the brakes. So these are really necessary to make the whole thing come to a stop. So they are now crucial for your calculations. So now that you have the nominal load that you want to attach, you also have to think about the accident strain that might actually be caused if you do the whole thing the way I've just described. And that, again, depends very much on the response time of the brakes. It might actually also depend on the frequency converter, but I'm not going to talk about that because that is a very much changing value and depends on the manufacturer. It's not actually very much researched on, but let's talk about the brakes. So now it is very much important. Is accident strain really relevant for design purpose? So is it bigger than double the nominal load? And I have to think about that also as an operator. People are saying, oh, I rest assured that they did it right, but that is not kind of like what I said. You know, are we safe sitting here? What I said in the beginning. That is usually what users say. Also, you have the chain hoist, you know, it has been tested. There is a seal, there's a sticker on it. So I assume it's correct. But you want to attach to it must also be able to do that. So I have to think about that kind of thing. So what is my lifting device doing? So what is happening if I bring it to an abrupt stop? Is that still working? What about the dynamic forces that come in? So does that really work also with the forces that I actually assume? So that is again the calculation. It's a lot of numbers. I threatened to do that, but I'll be very, very quick. I'll be very much skipping through that. I'm just going to tell you what it's all about. So if you're interested in that, just send me an email. I'll hand out whatever we know, and then the engineers among you can easily get into it. So we actually already took a look at that in 2009. And then we were really talking about that overlapping situation. And I was wondering, okay, I'm a designer for a show, for a scene in a theater. I want to fly with a car. I need a kind of lifting device to do that. And now I have to calculate that kind of construction. So what about that interface between the machine that I get from the mechanical engineer, between myself, that I actually need the construction for my specific show? And then we did basically the calculation. Basically, we said, okay, you have simple accidents train that usually is smaller than double the nominal load. That is what we found out. And that was the first approaches that we then arrived at. Then we took a further look at that, and then we went on calculating that, and we have even more numbers, even more complex and all that. And then we actually took a very intense look at that. And there is this kind of 500 kilograms, and then it's 1.2 meters per second. It's very much theater-based, but that is something that a lot of people do in the halls. It's something that happens quite frequently. Then I did the calculations. You can see that in terms of power, engine power, and then you see also at the points that you see, then we all heard what the load is. Then you also see what the motor actually, what the engine needs to basically let go in. And then you have the test one, and then you actually also see the test load, and then the test load that is 25%. You can see that again, the 5%, okay. And then you basically have these two critical sizes. So that is basically 70 Newton meters for the non-engineers. That is the numbers that you need to keep with. So that is what it is. So it's all perfect. So let's actually go on. Let's actually talk about things that we actually calculated, something that I don't actually get from a standard. So how quickly do I want to stop? And it says 0.3 meters, so 30 centimeters. In case something happens, you want the thing to stop. So is that important? Just imagine two panels, and they just actually pass each other, and you have your foot in between them. So you want to know how quickly can you make the panel stop, because you want to protect your foot. Because if there is this kind of circuit kind of element or kind of security thing must actually be installed, that must actually make sure there's also pressure that is 15 kilos. That is something that you don't want to exceed in terms of working on your foot, so that you just get a bruise but nothing more. So that is basically what you need in terms of the stopping distance. Could also be 15 kilos. You can agree on that, and then your mechanical engineer is just going to do the design. So we said, okay, let's work with 30 centimeters. Then you do go on. So then the delay in braking. So what would that actually be like, or what would that actually be in terms of making the whole thing stop? If it says 7.459 meters per second, again, for the non-engineers, the earth acceleration is 9.8 meters per second. So obviously what the flyers are usually saying. So additional to earth acceleration, again, 1g extra. So obviously that means there's 2g that actually work on the load that I attach to it. So that is almost a double kind of thing that you have in that case. Then it does actually go on. It is about the brakes. Obviously you have the brake, the torque moment. Then obviously you think, okay, 27 centimeters, that is when you actually arrive at a stop. And then obviously there's also the rope force, and that is again the 12,000 newtons. There's a lot of information on the gearbox, a lot of data again. So we have actually been saying a safety or security factor 2. That is what you need for the engines in terms of the nominal load. So for the dynamic force 2.2, so you say, okay, the gearbox is also perfect, the transmission. But again, you'll see that as soon as you go into the test load, the factor 2 is no longer achieved. And if you now say, okay, you assume you have a problem, and then you already arrive at 1.2. So you can see that that plant is just about, so we had the simple accident strain. So that is still just about what the norm actually wants. So what about the ropes? Very often say, okay, 12 times safety, that is for ropes. So now we usually say factor 10 is enough. So they actually changed that about the minimal break point, and that is a reinforcement that actually came into power last year. And then we did the calculations again. So usually we had a factor 17 for this kind of system. So you actually push the emergency stop, take out about phase or course a kind of accident, then security goes down to 7, which is below 10. However, that is still okay because our standard says you only need factor 2 for the ropes. You say, okay, you were lucky, so that is good. So you're fine. So that was very, very quickly in terms of the numbers.
Brake application time is important too. I have to know how quickly the brakes will respond in order to calculate the load in case of an accident. And what we can see here is that for the nominal load, for twice the nominal load, we had selected the transmission, and when it comes to the rope, the accident load may become relevant here. So we have 2 more criteria for decision making. What is a necessary condition here is that at 300 Newton meters the stop sets in. But the standard says we need 2 brakes, which is counterproductive. Because if these 2 brakes apply at the same time, they will amount to 600 Newton meters rather than 300. So the thing won't stop after 27 centimeters, but after 15 centimeters. And the stopping distance is key to the deceleration figure, the number of G's. Like with an airplane where you have a looping with centrifugal acceleration. And the faster that happens, the higher the force is. So if I apply 2 brakes on the system, the deceleration is much harder and the load on the entire equipment or system is much heavier. So we try to have an offset, a temporary offset between the application of brakes so they don't apply simultaneously. And the brake application times might be designed to be shorter or longer. So the first brake should have applied for quite some time before the second one comes on, thereby creating a soft deceleration curve. If I say I need a 2 or 3 kilonewton brake, that's fine. It's feasible and a certain tolerance must be accepted. But you don't want to have 250 Newton meters. No, but you can have, say, 360 Newton meters. That might be an option. As an engineer, you don't know whether this is acceptable. And what has not been considered in these approaches is softness, is suspension effects. And by the way, this is just an interim report from a research project, so we are just in the process of finding out about the deviations between actual and calculated behavior. So we actually took a fly system, we applied a load, and we applied a measurement device that we evaluated by means of a measurement amplifier, and the transmission rate to our computers was at 125 Hertz. So we measured 125 times per second. And this is something that we really need to see. I mean, in case of doubt, a shaft or screw will break in 1,000th of a second. So actually, you do need to calculate and factor that in. And this is what happens in case of such a trial. You can see the peaks. This is quite a standard rigging system, fly bar at the theater. And this is just medium speed, 50 kilograms, and stop category 0. And in order to show the acceleration, we started at point 1. This corresponds to the Earth's acceleration. And as soon as I say stop, the load pulls further downward, the beam bends, the machine is elastically borne and suspended, and all of a sudden we arrive at this peak factor 21.8, and we then move downward. First, I have a peak higher higher than the factor of 2. But then you can see how the oscillation harmoniously subsides over time, and in the end it's a perfect fit. So I can live with that because the impulse as such is something that my machine can handle. So much for downward movement, but now let's take a look at upward movement and a little faster movement. This graph is quite freshly produced. We have not yet fully evaluated it. We are working with negative and positive values here. You can see that there is a zigzagging shape because the transmission is not perfectly even, but as a result of these measurements, you can see that the load moves about like that, but we won't see that. Visually speaking, it's a harmonious movement. And then we have this upward movement. The load wants to go up even further, but all of a sudden the gravity force is gone, 10.81. Then we have a straight section where the earth no longer pulls on my load. The load is suspended, as it were, and after being suspended, after hovering about, as it were, it will slump down. And now we see a peak amounting to almost 35 meters per square second. So this is 3.5 times or even 4 times the Earth's acceleration as a result of this flight test. And now we have a rather uneven, not quite harmonious movement. The load, due to the suspension effect of the system, is pulled up again, and it slumps down again and is moved up again. The second peak is still quite high, but after a while the oscillation flattens out. And now we see a line which we really thought was astonishing. This is for downward movement. The load is pulled up again and then it falls back onto the rope. And here you can see the fourth characteristic. 500 Newton, 50 kilograms is our test weight. Then we have the accident. The load slumps down. It is stopped. It moves along a peak, almost sixfold this figure here. 800 meters per second, but for an artist, for an acrobat, it's nothing at all. They want it to be even faster. So here we see the peak, and then it moves up again, and then we have a very long straight line. Now, what does the system do here? It pulls the load upward, and even though we had been in a downward movement, we are back to the flight test level again. So we have the hovering or suspended state, and then there is the next slump, and then we see leveling out of the movement. Okay, for acrobats it's okay, but in real life you don't want to experience this. You don't want to be decelerated with such a high load and then be hurled up again and then fall down again. So you don't want to experience this as a human being. This is where we currently are, and there are well-known mechanical engineering companies that also deal with this issue. What we see here is good for and important for both load cases, for the mechanical engineer, for the construction people, for the test personnel, etc. For them it is important to know what their machine will do in case of an accident. Of course, with extremely slow equipment, it's not so much of a problem. But on Monday, I tested a major protection gate on a stage which went at 0.3 meters per second, and we got a counterweight that led to the rope slackening, and all of a sudden this heavy weight fell into the rope, as it were. This is a situation that you don't want in normal operation, obviously. So our current conclusion is that the accident load should be derived from the maximum brake torque, or from the flight test, or from damping of the cable. When it comes to relevant transmissions, we always have to define the protection target. When I'm standing on a cart and somebody pulls the cart during a stage show, for instance, think of Stephan Rolfes' show. You've seen people being hurled about. People tend to stumble, they fall off the cart, etc. So what does that tell us? You have a setup to make, and this setup, whatever it is, a cart or structure that is supposed to move from the left to the right on the stage, or else the rigging should be such that it doesn't move up and down too slowly because you don't want people to get bored. Now, if you want to stop these, what does your construction do? The reconstruction will try to stop it here, and you have to accept to be able to absorb the horizontally acting forces. Now, what is more dangerous? If you have your hand between the two LED walls, you don't want it to be squeezed. In such a case, a short stopping distance is key. But short stopping distances lead to extreme forces, and you don't want your rig to tilt over or to break down. We don't like horizontal forces in our structures. We prefer to do without them. So we really have to look into this in more detail. We have to define the interfaces very clearly, and hole operators that work with fixed installations should actually be very knowledgeable about their holes. They should know how they work in standard operation and in accident operation. So you don't want a situation where experts come for first-time acceptance and you have the experts calculating the times and the forces. They will give you a certain value to go by, of course, but if you have to go at high speeds, please consider, when considering what to attach to these ropes or whatever attachments, you should actually consider the horizontal stability as well as the vertical forces that might possibly act. And you don't want people to be hurled about on the stage unless if that is the purpose of the exercise. So actually, this is what we are working on, and for stage engineers, this is, of course, an important tool to carry out measurements. Okay, so I am at the end of my presentation now. Now let's go for some advertising. In June there will be the Showtech, and we will be present there as a university. So if you like to come to the Showtech, you're warmly invited. There will be an in-depth report on our research project given there. And now I would like to take any questions or comments that you may have, and I hope that I didn't roll you over with this engineering stuff. Thank you very much, Mr. Rolfes, for this wonderful technical presentation. We have an audience of experts here, and I'm sure that everybody was able to follow. Any questions? You talked about the system that we should keep an eye on, and the system includes static absorbance at beams, at the ceilings, etc. You seemed to have focused on your machine alone, but as a user, I need to look at the static surroundings too. And for a structural engineer, this is important to consider as well. In the end, you very often calculate on a static basis without any dynamic factors. Well, two more things I have to ask here. What calculation do you have to use, and what load do you have to insert in your calculation? As a mechanical engineer, I know about the loads, and I know what loads my system can take, so I'm quite courageous. I tolerate plastic deformations, etc. Mechanical engineers tend to be quite courageous, but structural engineers are a little more cautious. They have to base their outcomes on assumptions based on standards, and they tend to be conservative rather than daring. So if you have a point like that, you try to use specific ancillary values to consider the loads for mechanical engineering. But then they will still calculate based on their structural and legal assumptions and standards. Structural engineers have the possibility to play around with load combinations, and they have to consider probabilities of occurrence. So the probability that there is a meter of snow cover on top and all the loads will still have to be borne if they break down in an accident and you see the manager of the event coming in running everything full speed, this is a rather unlikely event. So you go by certain probabilities and you go by certain tolerances. But if you don't know your loads perfectly well, it's better to be conservative in your calculation. So the structural engineer typically goes by the normal load, 500 kilograms, and you add 20 or 40% from the dynamic forces. You take a factor of 1.4 as a worst case scenario, and this is the load case that he typically uses. So structural engineers do consider this, but they don't use a factor of 2. They don't go by a factor of 10 either, obviously not. Goodness, it will not actually help us if the regular beam just is designed for normal or standard safety. Any further questions from the round, from the audience? Is everybody happy? Well, if you want to have more detailed information, please let me know and I will email you more detailed data.